Hi, I'm John Collins, origami enthusiast and world record holder for the farthest flying paper airplane. Today, I'm going to walk you through all the science behind 5 stellar paper airplanes. Most of us know how to fold a simple paper airplane, but how is this flying toy connected to smarter car design, golf balls, or clean energy? By unlocking the principles of flight and aerodynamics, we could affect the world on a massive scale. And by the end of this video, you're going to see paper airplanes on a whole different level. So to understand how this flies, we're going to have to go back and look at this, the classic dart. I'm going to walk you through the folding on this really simple paper airplane. The classic dart is just a few simple folds done well. Sharp creases are the key to any paper airplane. There's not a lot of aerodynamics here, so it's really just about getting some folds accurate. 2 little adjustments are going to help this plane or any paper airplane fly better. Positive dihedral angle and just a little bit of up elevator. There are 2 key adjustments that will help any paper airplane fly better. The first one is called dihedral angle, and that's really just angling the wings upward as they leave the body of the plane. That puts the lifting surface up over where all the weight is, so if the plane rocks to one side, it just swings back to neutral. The other thing is up elevator, just bending the back of the wings upward just a little bit at the tail. So air will reflect off of that, push the tail down, which lifts the nose. Those 2 things will keep your airplane flying great. Let's see how this plane flies. To demonstrate, our producer is testing it in an enclosed environment. With the main forces acting on this plane to fly, this plane will travel only about as far as your strength can muster before gravity takes over. But that's the problem. There's too little lift and too much drag on this plane. The ratios are just all off. Drag is the sum of all the air molecules resisting an object in motion. That's why windshields are now raked way back on automobiles. That's why airplanes have a pointy nose, to reduce drag. You want to cut down on the amount of drag so that it takes less energy to move forward. And with any flying machine, even our paper airplane, drag is one of the 4 main aerodynamic forces. The others are, of course, thrust, the energy that pushes an object forward, gravity, which is, of course, the force that pulls everything toward the Earth, and lift. That's the force that opposes gravity. And when all 4 of those forces are balanced, you have flight. Here's how all these forces are acting on the plane. When the dart flies through the air, it uses its narrow wingspan and long fuselage with the center of gravity positioned near the center of the plane to slice through the air molecules. It's very sturdy and flies very straight. The problem is, it can only fly about as far as you can chuck it before gravity takes over. But once you put some aerodynamic principles to the test, you can find clever ways to make the plane go farther. What if we tucked in some of the layers to eliminate some of the drag and expanded the wings to provide a little more lift so that the plane can glide across the finish line rather than crash into it and explode? So what do we need to make this plane fly better? More lift, of course. But what is lift exactly? For a long time, the Bernoulli principle was thought to explain lift. It states that within an enclosed flow of fluid, points of higher fluid speeds have less pressure than points of slower fluid speeds. Wings have a low pressure on top and faster moving air on top, so Bernoulli, right? Wrong. Bernoulli works within a pipe, an enclosed environment. Faster moving air, in this case, does not cause low pressure atop the wing. So, what does? To understand that, we're going to have to take a really close look at how air moves around an object. There's something called the Coanda effect, which states that airflow will follow the shape of whatever it encounters. Let's look at a simple demonstration of these 2 things. Okay, 2 ping pong balls, right? Faster moving air between them, check. The ping pong balls move together, must be a low pressure, right? Wrong. That's where it gets confusing. So, as the air moves between the ping pong balls, it follows the shape of the ping pong balls and gets deflected outward. That outward shove pushes the ping pong balls together, inward. What we're talking about here is Newton's 3rd law, equal and opposite reaction. So it's not Bernoulli that causes the ping pong balls to move together, it's that air being vectored outward, shoving the ping pong balls together inward. Let's see how that works on a real wing. Notice how the airflow over the wing ends up getting pushed downward at the back of the wing. That downward shove pushes the wing upward, and that is lift. So if the narrow wings on this dart aren't providing enough lift, and the body of the plane is providing too much drag, what can we do? Well, we'll need to design a plane with bigger wings that slips through the air easily. Let's take it to the next level. This is a plane I designed called the Phoenix Lock, just 10 folds. It's called the Phoenix Lock because there's a tiny locking flap that holds all the layers together, and that's going to get rid of one of the big problems we saw with the Dart, where those layers are flopping open in flight. Now, what you'll see here in the finished design is that we've done two things: made the wings bigger and brought the center of gravity forward a little more, making the lift area behind the center of gravity bigger as well. It's a glider versus a dart. Normal planes have propulsion systems like engines that supply thrust. Gliders, on the other hand, need to engineer in a way to gain speed. And to do that, you need to trade height for speed. Let's take a look at what's happening with the new design. With the center of gravity more forward on the plane, this plane will point nose down, allowing you to gain speed that's lost from drag. And then, when the plane gains enough speed, just enough air deflects off of these tiny bends at the back of the plane to push the tail down, which lifts the nose up. And that's how the plane achieves a balanced glide. What the bigger wing area does is allow for better wing loading. Now, wing loading, contrary to popular belief, is not how many wings you can stuff in your mouth before snot starts coming out of your nose. No, wing loading is really the weight of the whole plane divided by the lifting surface. In this case, the wings of the plane, not buffalo wings. High wing loading means the plane has to move much faster to lift the weight. Low wing loading means the plane can fly slower to lift the weight. Since each plane is made out of the same paper, the weight is constant. The only thing that's really changing here is the size of the wings, and that's what's changing the wing loading. Think about things in real life where this applies. Look at a monarch butterfly. Really lightweight design, right? It's an insect, doesn't weigh much, and it's got giant wings. It just kind of floats slowly through the air. And then look at a jet fighter. Really fast, really small wings, just made to slice through the air at high speeds. That's really the difference in wing loading here. Big wings, slow; small wings, fast. Now let's go one step further and see how wing loading can affect the distance in flight. Watch what happens when the Phoenix flies. It just glides more, and that distance that it moves forward, for every unit of height that it drops, that's called glide ratio, or lift to drag ratio. Applying this to planes in real life, an aircraft might have a glide ratio of 9:1. That's roughly the glide ratio of a Cessna 172. So that means if you're flying that Cessna and your engine quits at an altitude of 100 meters, there better be an airfield or a cow pasture less than 900 meters away, or you'll be in real trouble. Modern gliders can have a glide ratio as high as 40:1, or even 70:1. Hang gliders have a glide ratio of around 16:1. Red Bull Flutog gliders maybe have a glide ratio of 1:1, but that's really more dependent on the ratio of Red Bull to red beers in their stomachs when they were designing their aircraft. Now we have a plane with much bigger wings that slips through the air a lot better, so we can use that thrust to gain a lot of height, and then efficiently trade height for speed. That is, use all that thrust to get some altitude, and use that efficient glide ratio to get some real distance. But there's a new problem. This plane just can't handle a hard throw. We're going to need a good amount of thrust to get it to go the distance. So if the Dart held up to a strong throw but had too much drag, and the Phoenix did really well with a soft throw but couldn't handle the speed, what we're going to need is something that's structurally sound that can handle all the thrust and still have a wing design that will allow us to create efficiency that will go the distance. Let's level up. This is the Super CANARD. The folding on this, deliciously complex. Squash folds, reverse folds, pedal folds, really interesting folding. It requires a high degree of precision, accurate folding, and symmetry. And what's special about it is it's got two sets of wings, a forward wing and a rear wing, and that's going to make the plane stall resistant. We'll talk more about that in a moment. We can see a few things here. Center of gravity is in front of the center of lift. Check. Can it hold together with stronger thrust? Yes. The winglets actually create effective dihedral, making the wingtip vortices shed more cleanly and control left-right roll better, making it more stable in flight. Wing loading? Well, the interesting thing is you can see the design of the Dart inside the CANARD, and what it looks like we've done is added more wing area to it. However, the CANARD design is much smaller than the Dart, so we're not getting a big advantage here in terms of wing loading. It's very sturdy, so it can handle a lot of thrust, so we're hoping it can go the distance. But what's really cool about this plane is that it's stall resistant. Let's take a look at what a stall actually is on a wing. A stall is caused either by too slow of an airspeed or too high an angle of incidence. Remember the Coanda effect. The Coanda effect is the tendency of a fluid to stay attached to a curved surface. When air travels over a wing, it sticks to the surface, and bending flow results in aerodynamic lift. But when a plane is traveling with too high an angle of incidence, the air can't adhere to the surface of the wing, so lift is lost, and that's what we call a stall. If we give the front wing on the CANARD a slightly higher angle of incidence, then the front wing stalls first. That drops the nose down, and the main wing keeps flying. And that results in a stall-resistant plane. Let's see this in action. Look at that, the stall resistance, that's actually working. But here's the problem. Way too much drag. All those layers we added to the front of the plane to make that little wing happen, really causing the performance to suffer here. So we're gonna have to get creative. Maybe even out of this world. Next level. This is the tube plane. No wings. It rotates around a center of gravity that isn't touching the plane, and it gets its lift from spinning. What is this sorcery? The folding on this paper airplane is entirely different from anything you've ever folded before, but it's actually really simple. You're gonna start by folding a third of the paper over, and then you're gonna fold that layered part in half a couple of times. You're gonna scrub that over the edge of a table to bend it into a ring, and bada bing, you've got a tube. Now, because this plane is circular and it spins as it's flying, we're gonna generate lift in a whole new way using something called a boundary layer. Let's see how a boundary layer works on another spinning object. How do boundary layer effects work? When enough air gets stuck to the surface of the ball, as the ball is spinning, it'll start to interact with the other air traveling past the ball. And the net effect is, with some backspin, the ball will rise instead of going down, and that's boundary layer. Everything in motion has a boundary layer. It's the microscopic layer of air that travels with the surface of a moving object. So when air is moving across a spinning surface, air on top of the ball is additive, and air on the bottom cancels out, allowing the air on top to wrap around and exit in a downward stream. That's Newton again. This is how baseballs curve, golf balls soar, tennis balls slice, and how UFOs traverse the galaxy. I made that last one up. That's going to be a whole other chapter on advanced propulsion and warp drive. Something really interesting happens to wings when you make them smaller and smaller. Let's go really small, something the size of a dust speck. It just floats right there in the air. It doesn't have enough inertia to even elbow air molecules aside. So the closer you get to the size of an air molecule, the more difficult it is to shove them aside and make your way through. There's a number for that idea. It's called a Reynolds number. And a Reynolds number just measures kind of the size of a wing compared to the substance that the wing is traveling through. A Reynolds number helps scientists predict flow patterns in any given fluid system. And flow patterns can be laminar or they can be turbulent. Laminar flow is associated with low Reynolds numbers, and turbulent flow is associated with higher Reynolds numbers. Mathematically, a Reynolds number is the ratio of the inertial forces in the fluid to the viscous forces in the fluid. In other words, for a honeybee flying through the air, it's much more like a person trying to swim through honey. So ironically, in this case, there's a lot happening on the surface level. Now the tube may not get us the distance that we want, but it does give us a real insight to what's happening really close up, right down there at the surface level of a paper airplane. So to recap, the classic Dart and the Super CANARD, big drag issues. The Phoenix and the tube, good lift, but they really couldn't hold up for a long throw. We've gone through all of this incredible aerodynamic knowledge, but the problem still remains. How do we build all of that into a simple piece of paper so that it becomes an incredible paper glider capable of real distance? Let's level up again. This is SUZANNE, and let's take a look at how this thing can really soar. It can hold up on a hard throw. It's slippery through the air and really optimizes lift to drag in a way that none of the other airplanes could. This is a surprisingly easy plane to fold, just a few simple folds, but the key here is to really make the creases flush and precise. The adjustment of the wings is also critical. Dihedral angle here becomes really important. So, taking into account everything we talked about, let's look at how this design actually flies. Reynolds numbers tell us the airflow may shift from turbulent at high speeds to more laminar flow at slower speeds. At launch, the flow is laminar only at the nose. Because of the Coanda effect, as the plane slows down, the air starts sticking farther and farther back on the wing. At slower speeds, the plane needs more dihedral to keep from wandering off course. This plane has more dihedral in the middle of the wing, where Coanda effect and Reynolds numbers have worked together to create smooth airflow. The center of gravity is forward. The up elevator lifts the nose, and now the glide ratio kicks in. This paper airplane has flown past the record distance by gliding over the finish line instead of crashing into it. Empirical evidence has shown us exactly how fluid behaves in an enclosed environment. Similar patterns that reveal themselves on a small scale become even more obvious on larger scale. And as we zoom farther out, we can see how atmospheric forces, gravitational forces, even the surface of the Earth itself come into play. And once we reach a deeper understanding of what we're seeing, that will allow us to unlock not just better airplanes, but potentially a way to build more accurate tools for predicting weather, a way to build better wind farms. Everywhere that fluid dynamics touches technology, there's an opportunity to make things more efficient for a greener, brighter future. And that's all the science behind folding 5 paper airplanes.